Hello, everyone. Thank you so much for the invitation to speak about the future of hemodynamic monitoring, one of my favorite topics. Before I start, let me briefly disclose the fact I'm today leading a consulting and research group based in Switzerland and where we focus on digital innovations with medical applications. So, of course, I don't have a crystal ball, but at least we can discuss together about current trends to get, I think, a pretty fair idea of what's going to happen within the next 10 to 20 years. And as a matter of fact, we did a survey a couple of years ago, and I believe it's still, or it remains the most recent snapshot of hemodynamic monitoring and management practices in ICUs. The survey focused on COVID-19 patients and showed that ultrasound techniques are increasingly used, not only to look at the lungs, like in this example, but also to assess cardiac function. So, of course, we all knew that echocardiography was used to assess cardiac function at the bedside, but we were a bit surprised to see that echo was used more often than the pulse pressure variation or the passive leg raise maneuver to predict fluid responsiveness, and more often than any other hemodynamic monitoring technique to measure cardiac output. So what's the reason for the rise of ultrasounds? I think it's a combination between training programs, which are today very easy to find everywhere, including on the web, hardware innovations, and I share with you here a few examples. You see at the top on the left-hand side a pretty light and easy to move from one room to the other point-of-care ultrasound system. You see a pocket-sized device. And you see a probe that actually can be connected to a tablet or to a smartphone. There are even today wireless probes available for echo evaluations. Smartware innovations, of course, and I have in mind first speckle tracking or strain echocardiography, which is, as you probably know, a new way to assess left ventricular or right ventricular systolic function. So the idea is to quantify myocardial shortening during systole. So it's expressed as a negative percentage because it's a shortening. Normal values run between -20 and -30, meaning that less negative values, for example, -15%, would indicate a decrease in contractility. So as just an example, a study where we used speckle tracking echo to assess both left and right ventricular systolic function pretty quickly and easily, because it's a combination of qualitative, it's very visual, but also quantitative information with a number. Software innovation, of course, have in mind AI and more specifically machine learning systems, which have been designed to facilitate and automate echocardiographic measurements. So let's start with auto VTI. You know the value or the clinical value of subarachnoid VTI. In patients with shock, if VTI is normal or high, most of the time the shock is related to vasodilation. If in contrast, you measure a low VTI, then it makes sense to measure changes in VTI during a dynamic test. Could be a PLR maneuver, could be a fluid challenge. And if you observe an increase in VTI, the shock may probably resolve with fluid. Your patient at least is fluid responsive. And if you observe no change in VTI, it's probably a cardiogenic shock. So very useful variable to assess in patients with shock. And so with my colleague and friend, Philippe Gonzalez from Lisbon, we recently tested a few hardware and software innovations. And so I'm going to start by this new software, the auto VTI machine learning algorithm, which is part of this point-of-care ultrasound system. So it's a neural network algorithm trained with thousands of cardiac images. It automatically detects the apical 5-chamber view and the left ventricular outflow tract. Then it automatically records a large number of Doppler signals and is going to select automatically the most representative. And it gives you at any time user feedback regarding image quality using color coding. So here's an example. You see a 5-chamber view. And once you are well positioned, once the probe is well positioned on the thorax, you get this green trapezoid around the left ventricular outflow tract. And then the system will automatically compute VTI over a 4 seconds period. So we recently compared this new machine learning algorithm to reference manual measurements done by experts. And you can see that both experts and trainees were actually achieving pretty good results. But I think that the most important information that trainees are able with this tool to measure pretty accurately VTI in critically ill patients. Another example is real-time LVEF, which is also part of this point-of-care ultrasound system. It's also a neural network algorithm, but this time it will detect automatically the apical four-chamber view, endocardial borders, and end-diastolic and end-systolic times from the mitral valve motion, so no need to record ECG simultaneously. Then the system will calculate left ventricular volumes and LVEF using the Simpson formula. Again, you will get user feedback regarding image quality using color coding. So here you see an example. On the left-hand side, very poor quality. You won't get any LVEF measurements. And then in the middle, fair, and on the right-hand side, it's good quality. In both cases, you will get LVEF in just a few seconds. The way it works is that you have continuous automatic border detection, like in this example. You see green, so good quality. You can rely on the measurements. Here is a different patient with obviously a decreased left ventricular systolic function. So we also tested this new algorithm in another clinical study, which is currently in press in critical care. And again, we observed that both for experts and novices, it was a way to assess pretty accurately left ventricular ejection fraction at the bedside in critically ill patients, many of them being mechanically ventilated. Interestingly, in this study, the reproducibility of LVEF measurements was better for novices with the machine learning algorithm than for experts who were doing manual measurements. Another study with a completely different system. It's a crystal-free ultrasound transducer, so pretty affordable. You can connect to any smartphone. We use an iPhone in this study. And then you have, or you upload, or you install on your smartphone a machine learning algorithm application developed by Caption Health. So we did another study where we compared measurements of LVEF with these, not wireless, but with this crystal-free probe. And we compared to reference manual measurements done with the ion echo device. And here are the results. So you see we observe a significant relationship, but it's not so tight. And if you look at the agreement, the Blondheim representation, the average difference between the two methods was 0, so pretty good accuracy, but with very wide or pretty wide limits of agreements from -17 up to +16%. So I'm afraid it's not satisfactory from a clinical standpoint. In addition, fully automatic LVEF measurements were possible in less than half of the study population. When it was not possible, you had actually to confirm the selection of images before the algorithm calculates LVEF. And when doing so, what I described in the paper as semi-automatic measurements was clearly not very good results with, again, pretty wide limits of agreements. So to summarize regarding AI and echo, I think these tools, this software have not been designed, of course, to replace echocardiographists, but to help them, in particular, trainees and beginners. But it's important to realize that all systems are not born equal, and so they all need clinical validations before being adopted in critically ill patients. The third big trend I'd like to discuss today is hemodynamic monitoring for the many. You probably know there are audits and surveys which have shown that hemodynamic monitoring techniques are not used as they should be, particularly in high-risk surgical patients where there is clearly evidence that optimizing hemodynamics is useful to improve postoperative outcome. It's particularly true in resource-limited countries, in low and middle-income countries. And so that's why I like very much this concept of frugal innovation. The idea is to do more with less and to get the most out of what we have or already use. So how can we get the most out of pulse oximeter? We usually use pulse oximeters to measure SpO2, but most of them also give you the peripheral perfusion index, which is classically used as a quality indicator for the PPG signal, but is actually a marker of peripheral perfusion. as would be a capillary refill time. So the peripheral perfusion index can be used to assess peripheral perfusion. It is used as well to quantify PVI, which is a place variability index, a surrogate for pulse pressure variation for the prediction of fluid responsiveness. Changes in PI over a short period of time can be used as well to actually estimate changes in stroke volume. This is a pretty nice study from the group of Xavier Monet, where they perform the passive leg raise maneuver and quantify changes in cardiac output or cardiac index and changes in perfusion index, PI, and showed that when you observe a significant increase in PI during the PLR maneuver, you can bet that your patient is fluid responder with a pretty high sensitivity and specificity. And similarly, if you don't observe any change in PI, very likely your patient is a non-responder to fluid administration. With machine learning systems, it's possible as well to extract or to predict blood pressure from the pulse oximetry waveform. If you feed a machine learning algorithm with a pretty large number of pulse oximetry waveforms and corresponding blood pressure values, then the algorithm will learn how to recognize specific patterns or signatures of changes in systolic or mean arterial pressure. And such a system has been used in this study from the group of Patrick Schottker in Lausanne to track changes in blood pressure during anesthesia induction. And you see that it was pretty useful to track changes in systolic pressure on the left-hand side or changes in mean arterial pressure. Once again, simply using the pulse oximetry waveform. So probably in the future, we'll continue in some patients to use a brachial cuff to measure blood pressure from time to time. But between two intermittent measurements, we'll have the privilege to or the opportunity to continuously track potential changes in blood pressure using the pulse oximetry waveform. How to get the most out of a brachial cuff? You may have heard about this new brachial cuff. High fidelity brachial cuff with a rigid shell, a conic shape, and an hydraulic sensor. Why high fidelity? Because that's the kind of signal you get. So in blue, in green, in black, sorry, you have what you get from a classical oscillometric brachial cuff. So you see a dramatic improvement in the signal to noise ratio. This is a first validation study published a couple of years ago in anesthesiology and comparing these or measurements done with this new high fidelity brachial cuff to invasive central measurements and showing a pretty impressive agreement, particularly for extreme values where we know that usually brachial cuff techniques are not reliable enough. The beauty as well is that because you get a blood pressure waveform, maybe it's going to be possible to compute pulse pressure variation and cardiac output from the appropriate pulse control algorithm, of course. How to get the most out of a Foley catheter? Most patients undergoing high-risk surgery and ICU patients have a Foley catheter in place anyway, so better to make it smart. Here's an example of a new Foley catheter integrating a PPG sensor for continuous monitoring of UPI, the urethral perfusion index. It has been used already in a few pilot studies. And that's clearly something we could envision to use to titrate vasopressors, to individualize vasopressor administration. Because we all know that sometimes there is a dissociation between blood pressure and tissue perfusion. You see here an example in a patient where when anesthesiologist administered norepinephrine, you see a rise in mean arterial pressure, but actually at the same time, you have a decrease in tissue perfusion as measured by the urethral perfusion index. Last but not least, disposable free cardiac output monitoring systems. I mean, they are already available on the market. And so they have the opportunity to go green, to decrease hospital cost, of course, but also to decrease plastic waste. From an economic standpoint, obviously very interesting. Here is a quick and dirty economic evaluation for an operating room, assuming one case of high-risk surgery per weekday, so a very conservative approach, and assuming that each disposable sensor costs around 120 euros. And as you probably know, it's very often actually more, but clearly it depends where you live and which system you are using. But based on these assumptions, we can easily estimate that the cost would be 5 times higher when using the disposable system. And if you use a disposable free system, you can drop the cost per patient around 25 euros, making hemodynamic monitoring system pretty affordable. So in conclusion, clearly the rise of ultrasounds, I'm pretty sure we'll use more and more point-of-care ultrasound systems in the future with smart algorithm, in particular machine learning algorithm on board. It's going to be extremely useful for beginners, for trainees. Then hemodynamic monitoring for the many. We need to ensure more patients may benefit of hemodynamic monitoring and optimization, particularly in low and middle income countries. To do so, we can rely on disposable free cardiac output monitoring systems. Useful to decrease cost, useful to decrease plastic waste, obviously. Hardware innovations as well. I shared with you a few examples. These new brachial cuff and these smart Foley catheters to assess continuously, non-invasively, automatically tissue perfusion. And of course, software innovations. I just gave you the example of blood pressure measurements from pulse oximetry waveforms. I think we'll get more in the future, but it was just to give you a flavor of what should be available in the next 10, 20 years from now. With that, I thank you very much for the invitation. Thank you.